Water is very important in industry for a lot of processes, such as the generation of electricity. 80% of the electricity generated worldwide is produced through the use of steam turbines via steam water cycles. Due to the ongoing shift towards alternative water sources, such as industrial or municipal wastewater, and the use of new water treatment practices in steam water cycles, different types and concentrations of contaminants, such as organic acids, chlorides, carbon dioxide, etc., are present in the water, which can lead to large problems. For example, due to steam water partitioning of organic acids, the first condensate formed in low-pressure steam turbines is typically acidified. This acidified first condensate can cause significant corrosion damage to the steam turbines, which might lead to an unexpected stop of the power plant and hence produce important operating losses. Corrosion can be defined as an undesired material degradation caused or accelerated by an electrochemical interaction between a material and its environment. For example, in acidic aqueous environments, reduction of oxygen and hydrogen protons can take place, which might lead to hydrogen embrittlement while metal atoms go into solution by oxidation. As such, the metal slowly dissolves in the water. In the lab, the corrosion rate of virgin metal samples in aqueous solutions can be determined. To mimic industrial conditions, the electrochemical cell is heated. By connecting a potentiostat and inserting electrodes in the cell, electrochemical measurements can be performed. When applying strongly negative potentials, electrons flow from the counter electrode to the working electrode, which is the metal sample. There, reduction reactions are favored. By making the potential more positive, the electron flow decreases. And eventually, electrons flow from the sample to the counter electrode. Then, oxidation at the metal surface is promoted and metal goes into solution. At the corrosion potential, the net current is zero. However, the corrosion current, which is a current at which both the cathodic and anodic reactions occur equally fast, is not zero. Knowing this, the corrosion rate can be determined according to Faraday's law. For example, by adding acids to the solution, corrosion reactions speed up and the corrosion rate increases. In order to determine the effect of the flow on the corrosion behavior, the metal sample can act as a rotating cylinder electrode. In this way, flow-accelerated corrosion can be investigated. Industrial installations are continuously under elastic stresses. A combination of material, environment, and the presence of stresses can lead to stress corrosion cracking. Therefore, in situ constant load tests in aqueous environment are performed to evaluate the behavior of materials under elastic stresses in corrosive environment. When the combination of material and environment is susceptible to stress corrosion cracking, subcritical cracks can form and grow, which can be studied by microscopy. In order to investigate to what extent the mechanical integrity of the material degrades due to the presence of the environment and stresses, the material can be in situ tensile tested in corrosive environment. For example, when acids are present in the aqueous environment, losses in ductility and strength are observed. Inhibition of corrosion can be done by adding film-forming products to the water, which can form a protective barrier between metal and corrosive environment. These corrosion inhibitors are validated in the lab and implemented in industry when showing an improved corrosion behavior, as such increasing the lifespan of the installations as well as reducing the impact of deviations in water quality.